Hello everyone. Today we are going to see what is the support in structural engineering. So this question is very strange. What is a support? Because everybody who has got the rudimentary knowledge in structural engineering knows what is a support in structural engineering. Well, you have got a cantilever beam. The one end of the beam is fixed. So that one end that is fixed, there is a support there. And you've got a simply supported beam where the beam is simply supported. There is a support on two ends of the beam. And you can have a fixed beam where the two ends of the beam is actually fixed. There is a fixed support there. But what exactly is a support? So we are going to see what exactly is a support. Hope this video may be a bit insightful. So to understand what is a support, we have to first define what is the stiffness, and I'm going to define stiffness with the help of a bar here. I'm going to consider a stepped bar. So here we go. This is a cantilever bar. Also, it is a stepped bar. And you can see that it has got two elements. So this is the first element of the bar. And the second element I'm going to draw by different color. Maybe look for red color. I'm going to represent the second element by a red color. There you can see that this is the second element of the bar. Of course, this bar is fixed on both ends. I'm calling this as a bar, not a beam, because the load that this particular structure will be subjected to is going to act along the axial direction. That's the reason why I call this as a bar. If the load is going to act along the vertical direction, I should actually call this as a beam. Now, obviously here in this case, it is quite obvious that the cross-sectional area of the first element is going to be greater than the cross-sectional area of the second element. So obviously the first one is going to beat the second one with respect to the cross-sectional area. And as far as the length is concerned, still the length of the first element is going to be less than the length of the second element. Okay. With respect to the Young's modulus, element number 1, let us assume that it is made up of a stronger material. So Young's modulus of the first element is going to be greater than the Young's modulus of the second element. That is the assumption. We know what is the formula for stiffness in the case of a bar. Stiffness is given by the expression AE divided by L. It all comes from stiffness. The general definition for stiffness is it is the amount of force that you have to apply to stretch a particular component. You may want to consider a spring, but by a certain magnitude. So that is what is called as stiffness. But you can write the force in terms of stress. Stress is force by area, so force is stress into area. And you can write deflection in terms of strain. So strain is change in length divided by original length. So deflection is strain into capital L. Okay, and you can write stress in terms of Young's modulus into strain. So there you go, Young's modulus into strain into A divided by E into L. So that's how you get this particular expression that we have. So it is A by L. All right. Now you can see that greater the area, greater the Young's modulus, smaller the length, then the stiffness is going to be greater. So obviously in our case, the first element has greater stiffness compared to the second element. So that is quite obvious. Now, the next point that I will have to say here is that let us assume that I'm going to apply a load right at the junction. I'm going to represent the load by yellow in color. So look for yellow color. Here we go. There you go. That is the load that I am going to apply. Now, because you are going to apply the load right at the junction, the one that has got greater stiffness is going to take more load. Okay. The one that has got greater stiffness is going to take more load, which means that the load is capital P is shared between elements 1 and 2. So let us say that element 1 takes the load P1 and element 2 takes a load P2. So P1 plus P2 is going to be equal to P. Okay. So in this case, P1 is going to take greater load compared to P2. Why P1 is going to take greater load? Because the one that has got greater stiffness is going to take the greater load. Now, let us push this concept to the extreme. Now comes the crucial point. Now what I'm going to do is I'm going to increase the cross-sectional area of this particular first element, I'm going to keep on increasing the cross-sectional area. So what should happen if I keep on increasing the cross-sectional area? The value of P1 should keep on increasing. So P1 should keep on increasing if I just keep on increasing the cross-sectional area of element 1. So at one point of time, what's going to happen is the cross-sectional area is going to be so high, okay, for element 1. Maybe I can represent that by green color. It's going to be so huge. And I'm going to keep on decreasing the length of element 1. So the length is going to be very small. It's going to be infinitesimally small. And the cross-sectional area is going to be very humongous. So the element 1 would look something like this, because its cross-sectional area is highly increased and its length is highly decreased. And element 2, which is shown by red in color, would look something like this. Okay. Now, what happens if I apply the load capital P in this case? Over here, if I apply capital P, then capital P will be taken by the element 1 alone, because it has got infinite stiffness. If you look very carefully at this particular structure, it looks like a support, right? Which means that by definition now, support is a structure with infinite stiffness. That is the reason why if you apply a load at the support is going to take all the load, because support has got infinite stiffness, which means that a structure that has got infinite stiffness is going to take all the load, which means here, if I apply the load here, then the load will be taken only by the support. Same way, if I apply a load here, maybe I can use a different color, maybe I can use blue color here. If I apply a load here, the entire blue load will be taken by this support here. So you can now say support is a structure, as an element with infinite thickness. Now there is a small catch here. Now just imagine I'm going to draw the front view of this support. Okay, if I draw the front view of the support, of course the cross-sectional area is going to be very high. This is the cross-sectional area. Comparatively, it's going to be very high. Okay, of course the length, the thickness is going to be very, very small. Okay, the length of the element is going to be very, very small. And just imagine that I'm applying a point load. So just to get across the concept, just imagine that the point load is acting like this. Now you may ask this question: when there is a point load that is acting on a thin structure with a huge cross-sectional area, then there is going to be a dent that will be produced in this region. So that is quite intuitive. But understand one thing, the assumption here is that it is a point load, but how do you think this load comes? This point load is not actually a solid chunk of load that is acting concentrated on one particular point. It is actually spread over the entire area. It is like a uniformly distributed pressure. It is like a uniformly distributed load that is spread over the entire area. And what is the resultant of all these uniformly distributed load? The resultant of all this uniformly distributed load is what is given by this particular big arrow. So this particular big arrow actually represents the resultant of all the uniformly distributed load. So just to avoid confusion, you can think of point load as not a solid chunk of load acting at one particular point. Instead, it is the resultant of all the UDL. Same way, this load, it is the resultant. This load, it is the resultant. Hope this video is useful. Thank you all for your patience.